So today's class, in today's class, we are going to be looking into the very popular problem that people often encounter. So it's a very old idea problem, very common in data science and machine learning modeling problem. So this is what we call the imbalanced data set problem. So because usually, as we say, always let the data speak. So this is part of our series on important clarification series. So meanwhile, last week we discussed with ourselves on how you can start your machine learning modeling in your own area, irrespective of your field of interest. You can easily use machine learning modeling to solve problem there, ranging from whatever you can actually think of. The capability is so unique. So we summarize the procedure that need to be taken for you to be able to solve problem using machine learning modeling in your area. To quickly recap, we said you have to identify your area of interest, look for free online data sets to start with, build your first machine learning model using the free data set from online downloads, do hyperparameter optimization, select better algorithm, do feature selections. After that, analyze and discuss your result, document your experimental outcome and findings, and then disseminate your result in case of you have interesting findings or improvements. And there are always ways of identifying the gaps that you need to solve. We also mentioned that the fact that the data set is from online doesn't mean that you cannot publish it as a researcher. No, it depends on what you are able to bring on the table after your experimental procedure. Now, we say based on the experience from the online data set, try to gather new data set related to this area of interest. You can gather your data set by contacting interested parties, established companies, or you can even use questionnaire interview to get your data set. We stress the fact that this is one of the areas people often neglect. See, you can get data set based on interview and questionnaire, and will make life easier, and will maybe take lesser time instead of waiting for a complete year without getting approval. Even after getting approval, again, it takes a lot of time before you get the data, and without the data, you cannot move further. Then we said do new modeling using the new data set, analyze, and then you move on. However, as simple as the procedural rules, so one is very simple but often misunderstood challenge is the imbalanced data set problem. On a regular basis, I get a lot of emails, question requests on how do we undo the imbalanced data set. You see, one of the pre-processing procedure that we have to pay attention to, or we can do without them up till a particular point in time. So now, the first thing which is very important is to always refer back to this machine learning modeling process. See, you have the data preparation. So where you get your data, you pre-process your data. There are several pre-processing steps. For example, you want to treat the missing value. We have discussed how to treat missing value in our previous videos. We can check them out. Treating missing value. Also, sometimes people try to normalize. You might need to normalize your data if this is necessary. And also, among the problems that we might face in this place is what we want to discuss today, which is imbalanced data set. Imbalance. So when do we say data is imbalanced? Is it compulsory? We have to solve it before we can do the modeling. See, once you have your data, it's always good to practice the principle I refer to as let the data speak. Let the data speak. When you say let the data speak, it means as soon as you get your data set, prepare it in a format that you can upload to the machine learning modeling platform like Weka, like Python, whatever area you want, it's always good to put your data in an Excel format and save it as CSV. So this makes it very easy for you to transfer your data and to be able to visualize and look at your data, say if there's problem with it, missing value, or thereafter. So the moment you have your data set, it's always good when you clean it, do the barest minimum of pre-processing, because pre-processing, these are called pre-processing. There are so many pre-processing you might want to do. But however, note that as you are pre-processing the data, you might be indirectly taking the data further away from the original data set. And it's always good to model the data let it be closer to the original data in the real world. Because after all, when you finish modeling, your model is going to be deployed in the real world situation. So we want the data to be as close together as the real world data set or real life data set. So because in the course of preprocessing, a lot of people, they engage in what could be referred to as data mutilation, and including so many fake data sets at the end of the day, which might affect the performance. So once you have the data set, let your data set go straight to data modeling. So then after that, check the performance. So you have that particular privilege of going back. You might have to go back again and tune the parameter, go back again and change the algorithm until you see the one that is working for you. And you also have that particular privilege of going back to feature engineering. You might have to even engineer the features totally. For example, you have date. There's a variable that is date, like where you have 20 April 2022. Then you might decide to engineer the feature, break it down into 3 features. Separate it, day, which is 20, month, which is going to be 4, and then year, 2022. Instead of treating it as one feature, you are going to treat it as 3 features. This is part of feature engineering process. You break them down to increase the granularity of your data set. So you have that freedom to go back and change it and do things and then go back. Even missing value sometimes might be optional. If you are aware that you have missing value, there are some algorithms like decision tree that will work for you even when you have missing value. So try to use decision tree even with the presence of the missing value and see if it works. Because the moment you start treating the missing value, replacing them with mean and so many other methods of treating missing value, you might actually end up adding fake data to the data set. It is when you cannot model anymore, then you go back again and treat your missing value, treat other stuff, and the likes. Even including the imbalanced data set we are discussing today, it could be actually optional in the principle of let the data speak. Because what is data imbalance? The data imbalance is a common problem in machine learning, modeling, and data science processes, which is where one class has a significantly higher number of observations than the other. See, you want to build a model, for example, that can predict if somebody is sick of a particular disease. See, like maybe heart attack. See, in an ideal society, so imbalanced data is a kind of natural system that you are expected to see in a normal environment. So when you bring up data for that, you are going to have class A, which we call positive. These are people that are suffering from that disease. Maybe you have like a 300 patient. They are suffering, confirmed by medical doctor that they are suffering from the disease. We got the data, but when it comes to people that are free, we call them the negative class. These are healthy patients. These are, healthy people, healthy population. Yeah, let's call it healthy population. So here you have like a 1,500. You see, I said this is a normal data set. So that is why we shouldn't rush into, we shouldn't see data imbalance as a big issue. It is a natural phenomenon because in a normal society, we want more people to be healthy and fewer people to be sick. This is a normal data set. So when you face this issue, this is what we call imbalanced data set problem. So you have the number of sick people is 300, and then the healthy people data collected 1,500. So when you train your model using this kind of data, there's possibility that this is going to lead to biased models, so that you're going to have poor performance on the minority class. Your minority class, the system will not be able to recognize the minority class. And unfortunately, here, the minority class, they are the sick people. Though there's going to be a lot of false negative. When you train your model and then test it, most likely it will be classifying everybody here as healthy. Everybody's okay. Everybody's okay. Because the model has been exposed to more sample from the healthy population, so it's able to recognize it easily. It might not be able to recognize people in this side. Sometimes the imbalance may be more. We have seen cases whereby we have only 10 sample here, and then 14,000 sample here. Imagine that kind of data set. 14,000 against 10. How are you going to train the model? But despite this huge challenge, it's always recommended that once you get your data, even when it is imbalanced, try to run the experiment first. Based on the principle of let the data speak. Pay attention to this. Run the experiment. Let us see what you are going to get. Because surprisingly, or in some cases, even with imbalanced data set, the algorithm you have selected might be able to model it. And we have gotten that. One of my student teams in the past actually got very, very imbalanced data. And when they modeled it, they were able to get 100% accuracy, F1 measure, all the performance measure were 100%. Excellent work. It's very rare to have such a case, but it is possible. So this is why if the algorithm can model it and get 100%, then there's no need to start thinking of how am I going to treat the imbalanced data set? Because the data outside there you are going to be modeling, they are imbalanced naturally. So if you can solve it without going through the imbalanced treatment at last, why not? So it's always good to, first of all, run the experiment using algorithm that might have the capability of doing that. But when it failed, this is why you can always go back. So after modeling with only sample 300 from class A and then 1,005 from the second class, you found out that you are not getting good results. Okay, you have to go back again. Then you have to tune the parameter first. Tune the parameter, maybe that's why you are not getting it. By running it at once, you cannot just assume you don't get it. I think I've stressed this before. If you run a model, you must make sure you do the parameter tuning or hyperparameter optimization before you can declare that the algorithm is not working. Otherwise, you are not being fair to the algorithm. In other words, you are actually lying against the algorithm because you didn't subject it to the proper procedure and you declare it as not fit for modeling the data. So that's not how to do it. That's not the correct practice. Correct practice is to do the hyperparameter optimization for it before you can conclude that, oh, after all this, we were not able to get good result. So if that happens after you have done that, then you can try to say, okay, what can we do? See, how do we identify the data imbalance? When and how to resolve it are some of the very important points that we have to pay attention to if we are aiming at getting higher performance outcome in our modeling. So where do we identify it? By mere looking at your data set in Excel, you can see that you are going to have a lot of 0, 0, 0. 0 means the person, these are healthy patients. 1, 1, 1 means people that are positive. You see that the zeros are more than the ones. And sometimes you have to look at your data description. Sometimes they represent the healthy people by 1 and the sick people by 2, depending on the people who supply the data set. But you see that one class is more than the other. But you shouldn't panic at this point in time. Let the data speak. Always remember this principle. So go ahead with your modeling, push it to the modeling stage. If there's no problem with the data, there's no dirtiness there, it's clean, but the only problem is imbalance. Okay, let it go. So you run your experiment, then you are getting the performance. Oh, it's not okay. we are not able to get something good. We are getting very low accuracy. And I will clarify later. In an imbalanced data set, you cannot use accuracy to judge, except if you are getting 100% accuracy. The moment you get 100% accuracy again, that means there's no problem. But however, if you get 99%, it may not be a success. Even when you get 99% accuracy, that's why I'm going to mention briefly before we end the section, what are the correct and better performance measure you have to look into. Now, so once you get to know that, okay, the data is imbalanced, we are not getting good results, then a particular measure you have to always watch out for is your confusion matrix. I think we have also described earlier how we can model the confusion matrix. And I want to believe we understand when we talk on imbalanced data set, we are talking of classification problem, which is by far the most common problem we are having. And every regression problem can always be converted to classification problem as an initial way of solving problem. You see, somebody wants to predict the actual grade of a student in the final exam, the final mark. Is it going to be 45, 55? Before you go there, because you need real number, this is also very tough to predict. Why don't you predict for us? Is the student going to pass or fail? This is yes or no. So when you solve problem, you make it multi-stage. Solve the simple one. Is it going to be true or false? Is it going to pass the exam or not? Then the next stage, you can try to predict the actual mark the student is going to get. So that's why classification is very, very important. In production system, in industry, they use this kind of classification problem to detect, is there going to be plant shut down or not? Is something going to go wrong in this plant for this week or not? So a lot of problems often got started with with classification problem first. Once you solve it, then you can move to the next stage. Okay, can we identify? If the model has identified that there's going to be a problem, then which part of the automation system are we likely going to have problem? Then the troubleshooting will continue from stage to stage until you arrive at your final destination. Now, so once you detected or you realize that there is data imbalance and you run the experiment based on the principle of data imbalance, then the next thing is to move further. Okay, how am I going to treat this problem? So that's after at least you have run the experiment one time. When? So because we've seen a lot of people, they will spend a lot of time, they never check it out, maybe it's going to work. And we have had evidences supporting the case that sometimes despite the imbalanced data, it can work. So after running it and make it not work, so don't spend too much time on imbalanced data treatment at the beginning before you even try out anything. That will be contrary to the principle of let the data speak, because maybe the data is very, very nice data, even while being imbalanced, you can get some information out. But when it becomes very clear that you need to treat the imbalance, then you have to now start thinking of how do we resolve this problem? See, there are several methods of treating the imbalance problem. However, making it very simple, the first one is to try to use this resampling method. So we have what we call the random oversampling and undersampling. Random undersampling and random oversampling. Oversampling is the undersampling is very straightforward. Undersampling means you just bring in your data set. We use a sample of 300 positive patients and then 1,500 healthy patients, the negative class. In this case now, undersampling means you try to randomly reduce this 1,500 to become 300. You can see, reduce this 1,000 to become 300. So by so doing, so you'll be having the same number, the same size of your data set. And then you can go ahead and do your training. And then finally, you have to do the testing. Whereas the oversampling method It's the opposite of what we've just did here. In the oversampling, so we are going to try to increase 300 to 1,500 randomly. Random increment. So why the 1,500 remains? Yeah. However, so once you do this, you have the same number of samples, then you can do your training and testing. However, something to be clarified here, very, very important. When you want to do, especially oversampling, please don't oversample, don't do the oversampling on the testing sets. The first thing is to, first of all, divide your data into training set and testing set. Why the data is imbalanced. Don't treat it at that point. So that you're going to have data, say maybe I have 70% for training, then 30% for testing. Before you treat imbalance problem. Because the testing set must remain imbalanced. I have to stress this. A lot of people that are making mistake here, they just balance the entire data set and then they divide it into two. In that case, you're already creating, because the real world is going to be imbalanced. When you get to the clinic, by the time you're going to deploy the new system, it's going to be working on imbalanced data set. So it should be able to identify imbalanced data set with many people that are not sick and fewer people that are sick. So the most important thing is the training set. You want the training set to be able to identify both the positive and the negative classes. So in that case, you have to duplicate the minority class. So the 70% for training, this is the one you are going to duplicate the lesser number to meet up with the higher number. But for the 30 or 20%, as the case may be, let's say we are using 20% for testing, that 20% should never be balanced. Don't balance it. Leave it as it is. However, I have to clarify one more point here. When you are breaking your data into training set and testing set, it's always good to use a principle that we call stratify. Stratify sampling approach. When you are dividing your data into 80% training, 20% testing, you have to make sure that among these samples, 20%, if possible, you should also have like 20% of the 300. Remember, we started from 300 against 1,500. Try to make sure that 20% of these 300 samples belongs to this 20% here. You see? Or at least reasonable percentage of these lesser values. Because if you break it, ignoring that fact, you might end up having 80%, all of them are coming from the larger set, 1,500 class. And then the other testing is not going to come from the other set. So stratified sampling approach ensures that, or make sure that we break our data set so that during the training set, the class A is going to have class A and B, we both be in the training, and in the testing set, both A and B also will be there. Both training and testing set, they are all well represented in a proportion, in a very correct proportion. This is called stratifying approach in breaking down data set. Now, having done that, the training set now, so during the after the breaking them down, maybe you have like 250 here, for example, for class A, which is the positive class, we have like 250, let's say sample. And here, as usual, we're having like maybe 1,300. Yeah, 1,300. Whereas here, we're having like now 50 against maybe against 200. 200 for the negative class and 50 for the positive class. This is still okay. Now you have this 250 against 1,300. Now you have to do the oversampling on this one. Repeat that 250 randomly until it becomes 1,300, just like the counterpart 1,300. Then you can do your training on this sample. While for this sample, don't do any balancing on it. Let it remain as it is. So once you build this model, now bring this original data set and apply it send it to the built model, and let it predict the outcome as the case may be. This is how you build the random oversampling system of balancing the imbalanced data. This is very important. It's a common mistake that people often make. They balance the entire data from the beginning, and then they divide it into two. So in which case, you are testing your model using data that is already balanced. And remember that you balance the data by repeating some samples, which means it's going to be a fake result at the end of the day. So, but during training, that is fine. So we let the testing set remain imbalanced, just like the way the real-life data set is going to be imbalanced. So this is a very, very important point that we are to pay attention to. So other method of doing this is a very common method called SMOTE. It's always available. It's synthetic minority oversampling techniques. They used to create synthetic data using some kind of resampling, special resampling method. And then sometime in a critical situation, we might also have to have what we call one-class classification or for solving an anomaly detection problem. So we have a one-class problem if the imbalance is really much, having imbalance of only one sample against several samples. Sometimes we also have to play with loss functions. So, however, the most important thing that I want us to take is how we break the data down is very, very important. So we have to balance the training set, but we have to leave the original set imbalanced. Otherwise, we are going to be working with fake data, which you can be getting 100% after you have done that, but then you are not doing the right thing. And a lot of people do make this mistake. So very important is also we have to pay attention to the evaluation metrics for imbalanced data set. Because when we deal with imbalanced data set, the metrics differ. So some of the important metrics we have to pay attention to include the F1 score, precision, recall, AUC or the AUCROC, the average precision score, and also please pay attention to your confusion matrix. Confusion matrix is always like this. See? So you start seeing something like this: 0, 1,500, and then 300. When you see this, the right diagonal here, they are the correct prediction. It means your model is able to recognize all the 500 negative samples as being negative. However, no single sick person was being diagnosed as sick. All of them were classified as not being sick, which is a dangerous mistake in medical prediction. See? So here there's no error, but here 100% error. It's not able to identify any of the minority class. So this is why we have to pay attention to them. And if you have, let's say we have 10 against 900, let's say we have like 990. There's a data set whereby the negative class is 990 samples, and the positive class is only 10. You run experiment on this kind of imbalanced data, you might end up having this. It means all the samples that belongs to the negative class, they are all correctly classified, but none of the positive class were correctly classified. They were pushed to the negative side, which means these are correct classification. This is error. You're going to have 990 out of 1,000 samples. You calculate the percentage accuracy, is going to be 99% accuracy. But none of the positive class is being correctly classified. You can see that's why accuracy is not part of what you are going to use to check the performance of your imbalanced data set, because it can mislead you. Imagine having 99% results in the testing, or when you are testing after building your model. So you will not even want to try anything. Oh, 99%, that is excellent. However, 99% means no one is being correctly identified as being sick, even when they were sick. So that's why we have to look at all these F-Mayor, precision, recall, and other things. And like I say, pay attention to the confusion matrix. No matter if you don't know how to interpret the statistical concept, at least you can see the confusion matrix. Anytime you see here, this is for two-class problem, this side, they are the correct classification. So we are expecting to have like 300 here, 1,500 here, 0, 0. This is excellent. This is kind of what we are looking for. That is, all the positive classes were correctly classified as positive. All the negative classes were correctly classified as negative. But in reality, we might not be able to achieve that. So, but in some cases, you might be able to get that. So we have to pay attention to what we are checking when we try to solve data imbalance, while also pay attention to how do we balance the data. So we should make sure that the testing data is taken out before we do the balancing for the training set, so that the data is not going to become artificial. So you have to try as much as possible that you are using data set that can be categorized as being original, close to reality of what you are going to use your model to identify. So this is what we are going to have for the day. So always remember, based on the principle of let the data speak, let the data speak. So start with data set, go into the modeling, then you can always come back to check. You have to come back here to do your data imbalance, and then finally pay attention to when you balance your data, make sure you don't balance the testing side. The testing side should be left as it is, as much as possible. Thank you very much for listening and for the time. Wishing you all the best. Thank you.